All right, so let's start. Welcome everyone to Calculus 3. We start with Chapter 1, Infinite Series. So when we learn mathematics in elementary school, we learn about addition of numbers, right? We can add two numbers like 1 plus 1 equals 2 and 1 plus 2 equals 3, right? So these are elementary arithmetic operations. But there are questions like very interesting questions like what is the result of adding an infinite numbers of numbers. So if we add one infinitely many times, right, then what do we get? Yeah. And there are questions like 1 plus 1/2 plus 1 over 4, which is 1 over 2 to the 2, plus 1 over 8, which is 1 over 2 to the 3, and so on. What is the result of this addition? So we add infinitely many times. And there are questions like if we look at the numbers like not irrational numbers, but sorry, it is a rational number. If we look at the numbers like 0.9999 and so on, is it equal to 1? Is it less than 1 or is it equal to 1? So we want to answer these questions, right? So for the first question, does anyone know the answer?
Infinity.
Infinity, right? That's correct. Because 1 plus 1 equals 2, and if we plus 1 plus 1 then is equals 3, then plus 1 equals 4. All right. How about the second one? One plus 1/2 plus 1 over 4 and plus 1 over 8. What is this number?
2.
2.
2. Right, that's correct. Very good. And how about the third question? Is it true or false?
True.
True, right? Okay, very good. So you see that these questions can be answered by by an argument which is quite intuitive, but not so rigorous, right? So we need some language so that we can describe the solution more rigorously. So uh, we need the language of sequences and series. All right, so when we study sequences and series, there are even more interesting questions, more difficult to answer. But when we study sequences and series, we see that we have very interesting identities like this, right? 1 plus 1/2 plus 1/3 plus 1/4 and so on. What is it equal to, right? And we have questions like 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on. What is it, right? And we have things like 1 minus 1/2 plus 1/3 and minus 1/4 and so on. Right? What is it? Right? And we will encounter many very, very beautiful identities. Such as this identity, 1 plus 2 square plus 1 over 2 square plus 1 over 3 square plus 1 over 4 square and so on. And there's an identity like this. This is equal to pi square over 6. This is an identity which was discovered by Euler. Very, very beautiful identity. So I remember in high school, I think I read a book and I met this identity, very beautiful identity. So with the language of sequences and series, with the theorems that we will learn, we'll know how to answer these questions. So let's start with the definition of what a series is. So I tend to use different colors for when I write. For example, I use different colors for definition, theorems, examples, exercises, formulas, so that you can see them more clearly. All right, so let's start with our very first definition. And this part of mathematics is actually very, very interesting, and they play a fundamental role in analysis. Right? So what you learn is actually called calculus, not analysis yet. The analysis that we learn, that people, the scientists use, more rigorous. They have epsilon and delta and things so on, and we'll get used to that later on. So let's start with the definition of a series of numbers. So so if we have a sequence of numbers, say un, right? If we have a sequence of numbers like this, right, then we can form a formal sum, right? We can form a formal sum. We can take out u1 plus u2 plus u3 and so on, right? So this is a formal sum. We can write it more shortly, like using the sigma notation. So sigma u of n is the formal sum. Right? So this formal sum is an infinite series. Right? So if we want to compute this number, we have to form the partial sums. Right? We form the partial sum, we call it S of n. Right? S sub n is u1 plus u2 to un. Right? And we check whether the limit of Sn when n goes to infinity is this. Right? So if this limit is this, right? So this infinite series we call it S. Right? S stands for sum. Right? We say that the series, the infinite series S converges. Right? And if the limit doesn't exist, then if the limit doesn't exist, we say that the series S diverges. Right? All right. So let's start with the very first example that we saw uh, at the beginning, 1 plus 1 plus 1 and so on. Right? So here un equals 1 for every n. Right? And if we have Sn, right, we have u1 is 1 plus u2 and so on until un. Right? So this partial sum is n. Right? So if we take the limit of this partial sum, what is it? Right? It's the limit of n as n goes to infinity, right? And it's equal to infinity. Right? So in this case, the series diverges, right? And it diverges to infinity. Right? So this is our first example. All right. So we have our next example, which is a geometric series. Right? So we have for simplicity, let us start with a series of 1 plus r plus r squared plus r3 and so on. Right? So in this case, we have un, right, equals to r to the n minus 1. Right? So our series starts with 1. here, sometimes people take a series starting with 0. The index starts with 0. It doesn't matter. You can use either way. In this case, we use un equals r to the n minus 1. Right? So the partial sum equals the sum of n equals 1 to infinity. I equals 1 to n. Right? I equals 1 to n of ui. Right? So it's the sum of I equals 1 to n of r to the n minus 1, r to the I minus 1. Right? Does anyone know how to compute this partial sum? What is it equal to? If we take the sum of r to the I minus 1, I running from 1 to n, what is this partial sum? Does anyone know?
It's 1 minus r to n over 1 minus r.
Very good, thank you. 1 minus r to the n over 1 minus r. Right. Excellent. Now we take the limit of n goes to infinity of the partial sum, right? 1 to the minus r to the n over 1 minus r. Right? So we suppose r is not 1, right? Because if r equals 1, then we have 1 plus 1 plus 1, and we know the answer already. Right? So if r is not 1, when does this limit exist? So if r is not 1,
when r is less than 1.
Almost correct.
And
How about
greater than 0.
right? But if r equals negative 1/2, is it does the limit still exist? If r is negative 1/2, minus 1/2, does it still exist?
No, it doesn't, because it depend on n. If n is odd number and if n is even number, it is different. So the
Right.
limit here doesn't exist.
Okay. So think about this. Negative 1/2 to the n, right? If n goes to infinity, it goes to 0, right? So it still exists, right?
I think we can consider the absolute of greater than 1 and smaller than 1.
That's right. Very good. That's the correct answer. That's the correct answer. So it exists when the absolute value of r, right? The absolute value of r is less than 1, right? So the series that we saw before, right? 1 plus r squared, right? So the series, call this series S, right? So the series S converges if and only if the absolute value of r is less than 1, right? And we want to compute this series as well, right? So in this case, this limit S equals the limit when n goes to infinity, 1 minus r to the n over 1 minus r. And this limit, it has to be equal to 1 over 1 minus r, right? So this is called a geometric series. Right? So this is the first example of a geometric series. So if we compute a more general series, if we take say a plus ar plus ar squared plus ar cubed and so on, right? So suppose a is not 0 and r is not 1, right? So this series is called a geometric series, right? This series is called a geometric series, right? So uh, sometimes I will give some terminology in Vietnamese for say so that you know both the terminology in English and in Vietnamese. So this series converges if and only if absolute value of r is less than 1, and the series is equal to a over 1 minus r, right? So this is our very first example of a series which we use a lot. Right? So there's another example of a series that we will use a lot. We'll we'll call it a P series, right? We call it Euler series because it was maybe invented, discovered by Euler. Right? So we take this sum, right? 1 plus 1 over 2 to the p plus 1 over 3 to the p plus 1 over 4 to the p. Right? We ask, does this series converge, and when it converges, what is it equal to? So there are two questions. The first question is easier to answer, and the second example is very, very difficult to answer. So we call this series, say, S of P. So people often denote it as, this is called zeta of P. So this series zeta of P converges, converge if and only if P is greater than 1. So when P is equal to 1, or P is less than or equal to 1, the series diverges. All right. So for this the result, we see the reason why it converges when P is greater than 1 later on. So until now we have learned the geometric series. Now we can see more clearly. So remember before that we have the series 1 plus 1 half plus 1 4 plus 1 8. We want to see whether the series converges or not, right? So here r is equal to 1 half, right? And a equals to 1. Right? So this series is equal to 1a over 1 minus r. Right? So 1 minus 1 half is 1 half. So this is equal to 2. Right? So previously we saw that this is equal to 2. Right? And now we see the reason why. Right? So you see that our language of sequences and series of partial sums allow us to compute an infinite addition. So you see that mathematics is very interesting. It introduces concepts that allows us to compute things rigorously. So sequences and a series allow us to compute infinite additions. Right. So there's this dictum that that you need to remember. This dictum that you see later on, right? So a series is a number. This dictum will be very useful if you remember it. Right? A series is a number. Why did I say why do I say that a series is a number? For example, you see that 1 plus 1/2 plus 1/4 and 1/8 and 1/16 and so on, right? This is an infinite addition, but actually it is a number. What is this number? It is 2, right? And if we have 1 plus 1 plus 1 plus 1 and so on, right? So what is this number? This is actually the number infinity, right? We add infinity to our number system, right? And now we add another kind of number, so like 1 minus 1 plus 1 plus 1 minus 1 plus 1 minus 1 and so on, right? So this guy is a kind of non-existent number, right? Non-existent number. Right? You can think of a number which doesn't exist, right? Because in this case you see that the partial sums s1 equals 1, s2 equals 0, s3 equals 1, and so on, s4 equals 0, and so on. So the limit of s sub n of n go to infinity doesn't exist, right? Because it's just the sequence 1 0 1 0 1 0. It doesn't have any limit. Yeah. So remember this dictum, right? A series is a number. Right? It may be a real number. It may be a complex number. It may be an infinite number. It may be a number that doesn't exist. All right. So any questions so far?
Thầy ơi, em không có câu hỏi nhưng mà chắc là do cái đường truyền mạng nó kém nên lúc thầy viết với thầy nói thì chỉ nghe đến tiếng rồi, còn lúc nào thầy viết xong rồi em mới thấy cái nốt của thầy ghi ra ấy. Nên thầy có thể viết trước xong rồi giảng đúng không ạ?
Ok, cái bạn nói là hoàn toàn đúng đó. Cái bạn nói hoàn toàn đúng đó, tại vì do cái đường truyền internet thôi. Cái này thì mình cố gắng chịu cố gắng chịu khó một chút. Ok, tôi hiểu ý bạn rồi. Để tôi sẽ cố gắng xem cách khắc phục như thế nào. Rồi, cảm ơn bạn. Cái này cũng rất là tốt. Rồi. Nhưng mà nãy giờ các bạn theo dõi có hiểu được tốt không?
Dạ, vẫn hiểu ạ. Mỗi tội là nó hơi chậm cái nốt rồi ạ.
Đúng rồi. Cái học online này đôi khi nó có một số cái tôi sẽ xem mình có cái nào khắc phục được không nha. Rồi cảm ơn bạn. Cái này rất là tốt. Cái câu hỏi của bạn rất là tốt. All right, so let's continue. So we have defined a series is so let's continue with necessary condition for convergence. All right, so the most important thing about a series, not the most, but the first important thing about a series. So two questions about a series that we need to answer. Two questions. So the first question is, does a series converge or diverge? So this is the first question. The second question is, if a series converges, then what is it equal to? So there are two questions, and more often the first question is easier, and the second question is more difficult. So the second question is often more difficult than the first question. Right? So we will try to answer these two questions in later sections, and we'll have many different methods to answer these questions. Right? So these questions cannot always be answered, but they can be answered in many cases using different methods. So our first theorem is about a necessary condition for convergence. So this theorem is called necessary condition for convergence. Rồi, hồi nãy là có bạn nói là cái đường truyền nó chậm á, thì bây giờ tôi sẽ cố gắng khắc phục bằng cách là tôi sẽ nói trước, sau đó thì tôi sẽ viết sau. Các bạn sẽ theo dõi được nội dung. Như vậy có được không bạn?
Dạ được ạ.
Rồi, ok. Bây giờ mình tiếp tục nha. So we consider a necessary condition for convergence. So we let sigma of un n from 1 to infinity be a series. You can call it infinite series, or you can call it a series. Right? And in this case, you understand it as a number, right? A formal number. Right? So if this series converges, say you call it S, right? If S converges, then the individual terms u sub n has to go to 0. So think about this. If you have u1 plus u2 plus u3 plus u4 and so on. Right? So these are individual terms, right? So plus u99, u100, and so on. Right? So if this series converge, then the individual terms has to be very small later on, right? So if you have something like if you have something like 1 plus 2 plus 3 plus 4 and so on, right? So this series cannot converge because the individual terms going to is going to infinity. So this series has to diverge because the individual terms do not go to zero. It violates this necessary conditions. Yeah. Or we have if we have a or if you have even like 1 plus 1 plus 1 plus 1 and so on. Right? So we saw before that this series diverges, right? Because the individual terms are going to 1, they are not going to 0. Right? So you see that the theorem says that if if the series converges, then the individual terms go to 0. But that is only a necessary condition. If the individual terms go to 0, it is not true that the series converges. It must satisfy some other conditions as well. So if we have if we consider the sum 1 plus 1/2 plus 1/3 plus 1/4 and so on. So in this case, the individual terms are 1 over n, right? And 1 over n goes to 0 as n goes to infinity, right? However, this is a p series with p equals 1, right? So remember the p series 1 plus 1 to the 2 to the p plus 1 over 3 to the p and so on. So this series diverges. This is because this is a p series with p equals 1, right? So this condition u sub n goes to 0 is true, but the series still diverges because it's only a necessary condition. Right? So remember that this implication S converges implies un goes to 0. Right? However, un goes to 0 it doesn't imply that S converges. Remember that. Right? So this is only a necessary condition, not a sufficient condition. All right. So any questions? So we can add or multiply add or minus two different series, right? So so if we have two series x sub n and two series sigma sub s sub n or sigma y sub n, right? So we can add or subtract these two series, right? So if the two series converges, then suppose that it converges. Then we can add or subtract, right? Then or we can multiply a series by a constant, right? So suppose a constant k is a real number, right? Then we can have a series sigma of k x sub n, and this is k times the series of x sub n. Right? All right, so let's continue with some theorem about the convergence of a series. So previously we saw a necessary condition. Now we will see some sufficient conditions, right? And our all right. So our first sufficient condition will be called the integral test, and it applies for positive series. Right? So let's a series sigma u sub n, right, is a positive series. So if the individual terms are positive numbers, it can be zero as well. Right? So actually, because it's equal to zero, I will not call it a positive series. Right? I want to be more precise. So let me call it a non-negative series. Right? And if it will be called a positive series if u sub n is greater than zero. Right? So if it is strictly greater than zero, we'll call it a positive series. So we have a theorem for positive series called the integral test, right? So this will be a theorem, right? So suppose f of x is a continuous function. And it is defined on the interval 1 to infinity, right? And we suppose that fx is non-negative, right? And we suppose that fx is decreasing, or actually is non-increasing. Right? So we will form a series by first forming a sequence, right? So u sub n is f of n, right? So the theorem says that if the integral from 1 to infinity fx dx converge, then the series sigma u of n also converge. And if the integral from 1 to infinity of fx dx diverge, then the series sigma u sub n also diverge. So if the individual terms are formed by taking the value of a function which is non-negative, then we can use the integral test. So remember that the function has to satisfy the conditions of the theorem, which is continuous function. Fx is at least 0, and fx is non-increasing. So if you want to use the theorem, you have to verify these conditions. So this theorem is actually very useful in many cases, right? So remember before that we have the P series, right? We have the P series. So okay. So we have 1 plus 1 to the 1 over 2 to the p, and so on. Right? So in this p series, the individual terms u sub n, right, equals 1 over n to the p. Right? So you can put fn equals fx equals 1 over x to the p. Right? So u sub n will be equal to f of n, right? So if the individual term, right, is formed by a function, then you can use the integral test. So in this case, fx is continuous function, right? So fx fx is non-negative, right? And you can see that for x equals 1, x at least 1, then fx is not increasing. Right? You can take the derivative to see that the derivative is less than 0. Right? So in this case, the P series, we want to consider whether it converges or diverges. Whether it's converge or diverge. Right, so we will check the integral of fx dx, right? If this integral converge, then the series converge. If this is integral diverge, then the series diverge, right? So this integral equals to the integral from 1 to infinity of 1 to the x 1 over x to the p dx, right? So can anyone try to compute what this integral is? Does anyone remember? So 1 over x to the p, we can rewrite it as say x to the negative p. So can anyone compute this integral? Can anyone check whether this integral converge or diverge? What is the antiderivative of x to the negative p?
If p is equal to 1, then it's the natural logarithm of x.
Say it again.
So we consider a case if p is equal to 1 and p is different than 1. If p is equal to 1, it's the natural logarithm of x.
That's very good. X to the minus 1 dx equals 1 equals log of x, and it diverges, right? And if p is not equal to 1, then so what happens when p is not equal to 1?
The integral equal to x to the power of minus p plus 1 over minus p plus 1.
That's very good. X minus p plus 1 over minus p plus 1, right? So minus p plus 1 over minus p plus 1, and if in this case, if you plug infinity in, right, then you see that it converge.
It converges when p is greater than 1.
That's right. And it diverge when
P is smaller than 1.
Very good. Thank you. Excellent. So you see that the integral from 1 to infinity, x minus p dx, right, converge when p is bigger than 1, and diverge when p is less than or equal to 1, right? So by the integral test, right, by the integral test, we will see that the sum of 1 over n to the p, right, has the same convergence or divergence. Right? Converge when p is bigger than 1, and diverge when p is less than or equal to 1. Right? All right, so now you can see that the fact that we mentioned about the p-series before can be proved by using the integral test. Right? So now this we have proved that this is true using the integral test. Right? So you see that the integral test is very, very useful. And remember, right? Uh, uh, so you need to verify the conditions are the hypothesis before using the theorem, right? Right. All right. So the P series was discovered by Euler, and Euler is also when P equals 2, right? When P equals 2, we have the series 1 plus 1 over 2 square plus 1 over 3 square plus 1 over 4 square, right? And it is also Euler who discovered that, who can compute this series, which is equal to pi square over 6. And this identity is absolutely beautiful, right? Because on the left-hand side is just rational numbers, right? 1 over 4, 1 over 9, 1 over 16, 1 over 25 rational numbers. But on the right side, you see that pi appears. Pi is an irrational number. So this identity is absolutely beautiful, right? So all right, let's
Is there a general formula for P series?
say it again.
Is there a general formula for P series to compute?
Yes, there is. There's a very general formula, but I will not introduce it here because I don't remember the formula. If you want a general formula, you can search. I think there is a general formula for the series 1 over 1 over 2 to the 2k plus 1 over 3 to the 2k plus 1 over 4 over 2k and so on. And these are actually called zeta values, right? Very interesting things, right? Very difficult to prove, right? You can search it on Wikipedia, right? You can search it. But yeah, I don't remember the formula. You need to check the Wikipedia. All right, so we have this integral test. Let us have a 10 minutes break, and then it's 9 a.m. now. We come back at 9 at 10 to 9, right? 10 minutes later. So let's have a break. I'll stop the recording.